All right, everyone. This is Carolyn Griffin with Riot. Thank you for being here today. We are super excited to have John Breitenbach from RTI, Real-Time Innovations. If you were not on the last Lunch and Learn, I'll just remind everybody that RTI has been a longtime sponsor of Riot, and John has been a longtime supporter. So we're very thankful to have him here today. Just a few quick reminders. This event will be recorded and posted on Riot's YouTube channel. Please, if you have any questions, put those in the Q&A box and we'll make sure to hit all of those at the end. And John will be demonstrating a live demo. If you look at his camera at the top, it is pointed at the floor specifically for his demo later. So he will make sure to bring attention to that once he runs it. But without further ado, I will give it to the man of the hour, John.
Thanks, Caroline. I hope everybody is staying healthy as we all do our part to flatten the curve and stay at home during this. So I apologize for the odd camera angle because of that. Normally we do this live, but unfortunately we can't do that today. So we're going to make do the best we can. So today's topic, we're going to talk about, the title of the talk is Edge Controlled, Cloud Connected. And it's really about design patterns for designing systems that for the industrial Internet of Things. Basically, how do we take these sort of edge systems, some of which we'll talk about in industries like energy and healthcare, and how do we connect these to the cloud to get the sort of broad connectivity that we want, while at the same time still meeting the real-time requirements that we have out at the edge. And so we're going to look at one particular design pattern called the layered Databus pattern today. But we're going to talk about some use cases, and as we go along, should you have any questions, feel free to put those in the chat window. And as Caroline said, she'll be collecting those, and as time allows, we'll go over those at the end. So for the talk today, we're going to talk about a number of different topics. We'll start by talking about Fitbits and Hyperloops, basically what's the difference between the consumer IoT and the industrial IoT. Then we're going to talk about the cloud. The cloud is sort of one of those generic terms that a lot of people use when talking about the IoT. So we're going to talk about what exactly is the cloud and what are some of the limitations of using the cloud as our main connectivity point. We'll talk about 3 different design patterns from the Industrial Internet Consortium. One of those 3 is called the layered Databus, and that's the one that we're going to take a deep dive into. And hopefully our demo will work today in this odd setup that we have. We'll see how it goes. And then, of course, at the end, we'll have Q&A. So first, I'd like to start by talking about some definitions. And I love this cover from New Yorker magazine because I actually grew up spent the first 40 years of my life in northern New Jersey, just across the Hudson River. So just right above the second R there in the word river is pretty much where I grew up. And I can tell you, having a lot of friends and family that lived in New York, this was very much their view of the world. You know, there was what was on the island, and then everything sort of across the river from New Jersey to Japan was essentially just sort of out there. And that's kind of the way in the IoT space that folks think of the cloud, particularly folks from the IT side of the world, right? The cloud is where the action is, and everything else, the edge, is just sort of out there. They don't really know where, but it's not here, it's there. And folks that work at the edge, folks from the OT, the operational technology world, the folks who keep the lights on, right, that run things like power systems, basically all the mechanical systems of the world that keep the world spinning, they have sort of that same view of the cloud, right? They're out at the edge and they're used to all their local field buses and devices. And to them, the cloud is kind of out there. It's just not here, it's there. And that's the sort of point of view that folks that work on the cloud side and folks that work on the edge tend to have towards each other. So it's important that we define the terms. For the purposes of this talk, the cloud we can consider some kind of elastic computing environment that's you know, in a large data center somewhere. So this is your Amazon Web Services, your Microsoft Azures of the world. IT, information technology, is the traditional computer technology that we have always had back when we used to have offices that we could go to every day. We were surrounded by IT. How does our email infrastructure work? How does our connection to the internet work so that we can surf the web and all those kind of things? The word things is highly overloaded in the IoT world, but basically these are devices, physical devices that have some kind of computing capability in them now. It could be small, something like a Raspberry Pi like you see here on my desk, or large things like autonomous vehicles and multi-million-dollar medical devices. OT, again, refers to those sort of out at the edge communications technologies that are in things like SCADA systems and industrial control systems today. The edge, again, is the IT's collapsed view of the world, right? To the cloud, the folks in the cloud, IT to them, or the edge to them, rather, is everything west of the Hudson River. And they largely collectively refer to that in a lot of cases as fog. And the fog is basically all of the computing elements that are outside of the data center that make things happen out at the edge. And this can be layered, as it typically is. It tends to be a multi-tiered design. So IoT is basically a collection of all of the above, right? Everything from the cloud to the edge. It encompasses things like IT and OT and fog technology. And that can, the generic term IoT can include both consumer goods as well as industrial goods. And then there is the IIoT, which is the Industrial Internet of Things. And this is basically IoT technology that consumers don't buy, with the possible exception of things like autonomous vehicles, auto-driving cars. So today, we are going to focus very much on the latter of these, basically the industrial IoT. So again, consumer IoT space is things like your Fitbits, your Apple Watch, your smart Nest thermostats. And the IT is more the things that you see on the right, the big spinning things of the world that basically keep us moving, keep the lights on, allow doctors to treat us and have good outcomes. So while 80% of the hype is focused on the sort of consumer IoT, because these are the kind of cool applications that people write stories about, 80% of the value and 80% of the business opportunity is really in the industrial IoT. If you look at industry analysts like Gartner, they all say that there is just a huge, huge opportunity in the industrial IoT. So today we're going to focus specifically on that and design patterns for that. Within the industrial IoT, there's basically three main types of applications. The first of these is your basic device monitoring. And this is essentially like a telemetry type application. You have some device out in the field, you want to access its status remotely. And so we put something simple on it that can push data up to the cloud. And this is very much a south to north transmission of data, really one-to-one, one individual device out in the field connecting to up in the cloud. And this is the kind of thing that we used to do when I first started in this industry in the mid-'80s with dial-up modems, right? We put them on cryogenic gas tanks and had them call back into the manufacturing facility where they made cryogenic gas so that they could basically produce on demand and dispatch on demand. So people are doing the same things today with IoT. This is the sort of very first low-hanging fruit, if you will, of industrial IoT applications. Simple monitoring of one or more devices back at a common spot. The next layer of sophistication is really what we call analytic optimization. And this is where we have a large-scale system already in place, perhaps an industrial control system at a plant somewhere, a large SCADA system. And it's been installed there for a while. It's running on legacy technology like perhaps PLCs, maybe a technology like OPC, which is used very much in that world. And we might take some of that data. Basically, this system is able to more or less run on its own, and it has previously. But we're going to take some of that data now and push it up to the cloud and run some analytics up in the cloud, basically as a way to try and optimize the system out at the edge. So it's really about optimizing things that already exist. We've got these legacy systems, and we're going to start to gather the data, distill it a bit, and use that to help us make better operational decisions out at the edge. And then finally, the hardest types, the most exciting types of applications for the industrial IoT are what we call edge autonomy. And these are basically entirely new types of applications. This is new functionality where it didn't exist before, and this is really about realizing the potential of smart machines to help mankind. And this is where we start talking about things like autonomous vehicles, right? Modes of transportation that are completely different now that can work on their own. This is where we start talking about autonomous healthcare, where the devices that are connected to a patient and monitoring their physiology are no longer just sort of passively monitoring the data and passing it off somewhere. Now they're able to take active control and have a positive net outcome on the patient's health by doing some local control without the need for intervention of a human necessarily in the loop. And we'll see why that's important in some of the upcoming slides. And so edge autonomy is a place that's very exciting to RTI. It's where we spend most of our time working. We work on lots and lots of autonomous systems, everything from autonomous cars, like I just talked about, autonomous transport, to smart connected healthcare, to the next generation of the electric power grid that leverages heavily newer technologies like distributed energy resources in the form of solar and wind, so we can start weaning ourselves off of carbon-based fuels. So let's talk about the cloud now. What are some of the problems if you're trying to do autonomy with using the cloud? Well, there's a lot of problems with pushing our data up to the cloud to some remote location. The first is that you can't always see it. I have what I call here in my house, since I've been working at home, I'm on cable broadband. And so I am sharing a pipe with all the other people in my neighborhood. Before COVID-19, that wasn't a problem because during the day, I pretty much had the pipe to myself. But now my whole neighborhood is home and working from home. And I can tell you in the morning, my internet weather report is very poor. If I run speed tests, then basically I can see that I don't have as much bandwidth as I used to have before everybody was working from at home. And then there's also times where it just goes down and I have no internet access, and that's a problem. So I have in my house Ecobee thermostats. They're like Nest thermostats, and normally I can connect to them with my cell phone, and I can do things like check my thermostats and my temperature and all that, and control the temperature in the house while I'm away. But every now and then something happens and their server is down. There's some connectivity issue that's a problem somewhere in the internet. And this is the story. I no longer have control of the temperature in my house from a remote location like I normally do. And when that happens, this is pretty much what my kids tell me I look like, you know, old man yells at cloud. I get very frustrated, right? Because I'm disconnected and I'm used to always having that always on connectivity. But the fact remains that today connections to the cloud can be spotty at best, and the performance varies widely throughout the day. I should point out that computationally, it's expensive to get there and back when it comes to communicating with the cloud. There is an expense both in time, in terms of latency, and an expense in volume, right? We have a lot of data. It becomes very difficult to shove all of that data up to the cloud and back in any kind of timely fashion. So what are some of the options there? And let's try and quantify that. So in terms of expensive time, let's take a look at a use case of an autonomous vehicle. An autonomous car traveling at 40 miles an hour covers roughly 60 feet in about a second. Or you can think about that as basically every 0.017 seconds, it's going to travel another foot. You think about how fast it takes for the human to blink an eye, basically an autonomous vehicle traveling at 40 miles an hour is going to be halfway through an intersection, literally in the blink of an eye. And so the question becomes, can we, for instance, if we were taking all the sensor data off the autonomous car, could we push it all up to the cloud, make the decision in the car, or in the cloud, and then push that data back out to the car to have it apply the brakes? And the answer is no. And it's no because of problems with latencies, round trip time to and from the cloud. That time, again, can be widely variable, anywhere from 20 milliseconds to up to 2 seconds to send a message up to a cloud server and get it back. And it is widely variable. So it's certainly nothing that you would want to rely on to make a decision that needs to be made in milliseconds. And so that's part of the problem of the expensive time when it comes to communicating with the cloud. There's also the problem of volume. This table shows typical volumes in the far right corner, far right column, of the various data sources in a typical autonomous vehicle. So between the cameras, the LiDAR sensors, the radar sensors, ultrasonic, GPS, and then our internal communications for doing things like commands, this is very high bandwidth data. It's spewing out lots and lots and lots of data every second. To the tune of over 10 gigabits per second is the average of what an autonomous vehicle generates, 12 gigabits per second. So clearly we can't push all of that data up to the cloud. You know, again, at 12 gigabits a second, you have to understand that people think that, oh, well, we'll throw 5G at it and 5G is going to solve all the problems. But for a single autonomous car actually exceeds the theoretical top capability of a 5G cell, right? Its capability maxes out at 10 gigabits per second. So just a single car would overwhelm a single cell tower, let alone hundreds of cell towers. So the point here is that there's no way that we can push all of this data up into the cloud in any kind of realistic fashion. We have to figure out how to do control out at the edge, handle that 12 gigabits per second out at the edge, and then maybe pick some subset of that to surface up to the higher levels up in the cloud. So again, to summarize sort of why you need edge control as opposed to doing your control out in the cloud, really it's about latency, throughput, data volume, and it's also about safety and resiliency, right? If we're intermittently disconnected from the cloud, safety and resiliency become a concern. And since the time that I originally gave this talk last year to some of the folks down in Charlotte for Riot, the world has changed. We live in a new world now in terms of safety. With the advent of COVID-19, we have a whole new set of problems, for instance, in hospitals. Those of you that tuned in earlier saw my desktop, and one of the young ladies in that picture from one of my family camping trips is my niece Mary, who is a recently pinned nurse. She got her nursing degree last year. She works in the emergency room. And so she is on the front lines of this COVID-19 response. And one of the problems that they have today, this is a typical ICU ward, and you will see on the screen on the left-hand side, there is a stack of infusion pumps, those blue and white boxes that are going vertically on a pole. And basically, they're all pumping, each one of those is pumping a different fluid into the patient. In the background, you'll see this patient is also connected to a ventilator. You can see the light blue tubes that are running up to him, and then you see some patient monitors there as well. All of these devices today are what I would say are dumb from a network connectivity standpoint. They don't communicate with each other. They don't communicate necessarily outside the room. So anytime that there's an alarm that goes off on an infusion pump, anytime that a set point needs to be changed, somebody like my niece Mary has to go into the room and fiddle with the front control panel of these things. That puts her at risk, and it puts the patient at risk. And it's become such a problem during COVID-19 that there have been cases, particularly in New York and New Jersey, where they were just, the ICUs were just swamped, and they were really trying to contain this, that there was an effort to physically pull the infusion pumps out of the ICU rooms and keep them in the hallway, and they just ran the tubing in. Well, obviously, that creates a whole different set of problems. Now you have tubes that are running 20 feet, and they don't infuse the same way as they do when they're mounted here on a pole next to the patient. And this is all strictly a communications problem. So we need a way to get these devices to be smart, to communicate with each other, to be able to communicate remotely to a nurse outside down the hall in a safe space at a nurse's station, as well as potentially up to the cloud, so that doctors can look at this information remotely, begin to treat patients remotely. And in the case of a pandemic like COVID-19, we can also take some of that data and surface it to even higher levels in the internet stack and out to the cloud and begin to share data across hospitals, within localities, throughout cities, regions, up to government agencies and world agencies like the World Health Organization, and get all this data live. But the question is, how do we partition the system to do that? There's some problems. You know, we could say, well, we can connect all these things and push it up to the cloud, but that's really not a viable solution to connect each and every one of these devices directly to the cloud, because essentially, if you do that, you have now placed every one of those infusion pumps, the ventilator, all of the devices in this room, you have placed it directly onto the public internet. And that, from a security perspective, is not a good thing. Every single one of those becomes a target for a hacker. So ideally, you want them networked locally at the edge, within the room, within the hospital. You want to collect and aggregate some of that data, perhaps downsample it, and then share that up through a secure pipe to somewhere off-site. You don't just want to connect these things directly to the web and start pushing the data up. So that's the problem space that we're dealing with today. So let's take a look at a demo, and that's why my camera is at this odd angle. I apologize for those of you looking for me. I am here, but the camera's just a little fiddly. So for this demo, basically what I have on my desk is I have a Raspberry Pi. This is, you know, a little $30 single board computer that's buried in there. It's just representative of an embedded device. To that, I have connected, this is a camera. It's basically an imaging sensor. This is called a PixieCam. Basically, it has the ability to sense and detect objects. I'm just going to use this as an example of some kind of sensor that spits out a lot of data. This is going to be doing 60 frames a second. But you can also think of this as the equivalent of something that would, for instance, monitor that patient in that healthcare situation and provide waveforms of their physiology, their pulse rate and respiration, and so on and so forth. So just translate that as a sensor to whatever your application happens to be. And then I'm going to show that setup of the camera to the Raspberry Pi talking on a local edge data bus to some other applications. I've got some visualization apps that I'll pull up, and in a second we'll actually run a control loop over the local network, and you can see that run. So let me hide the presentation and bring over some additional tools. Okay. Oh, and incidentally, the young lady here with the blue ball cap, that is my niece, Mary. She's the one that is a newly pinned nurse. And in her short time as a nurse, she has already been through having to live at the hospital for over a week during the last hurricane down there, and now COVID-19. All right, so over here on the right, I have a application called Shapes, and this is basically just a way that we can visualize the data coming in from the sensor. So as I move the object in front of the sensor, you can see that we're able to transmit the data across the network and visualize the data, visualize where the ball is in space. So I realize that there's probably a little bit of lag on the webcast, which is actually kind of the point of this talk, right? There is lag, there is latency, there is delay when we're trying to push a certain amount of data up to the internet. And so if you have needs for real-time control out at the edge, that latency, that jumpiness, essentially is unacceptable in any kind of real-time control situation. So this other window that I have here on the left, and actually let me fire up a couple of different instances of Shapes. We'll get them started in a second. Actually, let me resubscribe to that. So I'm just getting this set up correctly so we can do the visualizations that I want. Okay. So we have one application up top that's subscribing. I can have another application that is receiving that data, but perhaps in an entirely different way. I'm going to set this one up also to receive. Maybe this one gets a longer history. And maybe it's only interested in the data when the data is in a certain range. And that's represented here by the shaded area. So when the ball is low in the field of vision, this middle application doesn't get it. And then finally, we'll fire up another instance here that is subscribing to the same data. Maybe this one is going to do a short history and only get 4 updates a second instead of 1 at the full 60 hertz. So what we've got set up now is using this technology that called DDS, Data Distribution Service, and a Databus. Essentially, we have a local control network out here at the edge that is going between the Raspberry Pi that we have here, my desktop computer, and a number of clients running on that. So in the case of our hospital example earlier, you can imagine this is the sensor and the Raspberry Pi are connected to the patient. There are various patient monitors. And this sensor is going to share data with multiple other people on the network. That could be other devices connected directly to the patient so that those devices can start to cooperate directly without human intervention. Today, if somebody makes a mistake and puts an incorrect set point into something like an infusion pump, they can effectively cause the patient to stop breathing, right? If you infuse the patient with too much of a sedative, they'll stop breathing. And today, there is no connection between that infusion pump and, for instance, the respirator or the patient monitor. But what we should have in an ideal world is that the patient monitor, the thing monitoring the patient's vitals, should be in communication with all of the devices that are basically infusing medication to the patient. They should be in touch with the ventilator, and all of those things should work together automatically without doctor intervention, without nurse intervention. One of the biggest problems that they have today with all that human intervention is basically alarm fatigue. Every time a patient rolls or twists or does something in the bed, perhaps the blood ox level sensor on their finger becomes loose and it sets an alarm off down the hall. And so the nurse comes down the first couple of times to check on the patient, and pretty soon they get what's called alarm fatigue. And they start to say, oh, the patient in room such and such is just rolling around again. And so that leads to preventable human errors. There's no reason why all these devices talking together shouldn't be able to handle those kinds of situations on their own and make intelligent decisions locally. But the trick to doing that is to be able to distribute the data in a unique way to each individual client that needs it. So different devices connected to that patient might need data in different ways. And that's basically what we're visualizing here. At the top, we have one subscriber that just needs a little bit of recent history, but it needs it at a high rate. In the middle, we have a second client that's connected to the same sensor, and it's getting data at a high rate, but it's filtered. It's only getting the data when it's in a certain range, right? So only tell me about the patient's, let's say, the waveforms for his pulse if their pulse rate gets above a certain rate. So basically, if it gets up into that shaded area. Other than that, I don't need the data. If the patient is normal and healthy, I don't need anything. And the bottom one is basically doing downsampling. It doesn't need the data every 60 or every 16 milliseconds, the full 60 hertz frame rate. In this case, it's actually downsampling, and it's only getting 4 updates a second. And this might be an application that, for instance, is going to forward the data perhaps to somewhere off-site, right? Again, we can't push the full bandwidth of data up to the cloud, but perhaps we can do a downsampled version of this up to the cloud. And so this technology, the underlying technology here at Databus, is what allows us to do that. I haven't had to go back and make any changes to the original publishing app that's running down here in the Pi. I can connect an arbitrary number of clients to it that all subscribe in a way that makes sense for them in terms of rate, in terms of content. They are able to selectively choose all of those things and get the data fed to them just the way they want through this connectivity platform called DDS, Data Distribution Service. So this tool allows us to visualize a system like that. And the reason that DDS is able to share data with just who needs it, just when they need it, just how they need it, without us having to go back and change any code, is because DDS is what's called data-centric. And that means that DDS knows and understands the data types that are being communicated throughout the system. In other communications technologies, if you've ever done any kind of programming with, let's say, raw TCP sockets, or if you've used a technology like MQTT, those are not data-centric. The communication stack doesn't know what your payload is. It has no idea what the structure and schema of your data that's being transferred is. DDS, by contrast, is data-centric and data-aware. And I'd turn your attention here to the bottom of the screen, this bottom panel where I'm moving the highlight. As you can see, this tool has basically just plugged into the network and plugged into the Databus and said, all right, what kind of topics are out there? And it's learned that there is this topic called circle, and that topic has this data structure. It's got a string field called color, and that is basically a key field. That's how I can tell green balls or green circles from red circles. It knows that each circle has an X and a Y location represented by a long integer. It knows that each shape has a size represented by a long integer. As I move the ball closer and farther, you can see that the size changes. It knows that each shape can have a different fill kind, solid, transparent, or hatched vertically or horizontally, and it can also have a rotation angle, which is represented by a floating point number. Because the communication stack knows and understands the data type, it enables filtering like we see in this middle panel over here, where a particular application can basically request from the middleware data that only meets a certain criteria. And those content filters are available per subscriber, right? So different subscribers can subscribe to the same data with a different content filter, and I'll restart this bottom client with an entirely different content filter, and we'll still use it in conjunction with that time-based filter. But basically, this bottom application now is going to receive an entirely different data set from the top application or from the middle application, right? The middle application now, the ball is outside of its field of view, so it's ignoring that data. This is a different device in the system that only cares about this particular sensor data when it's within this shaded area. And so it gets data totally differently. And again, I haven't had to make any changes back to my original publisher of the data. Essentially, I can design one simple device, publish the data, and anybody that wants to subscribe to it can subscribe and filter it and downsample it and do whatever they want to do in their own way. And this allows us to build very nice modular systems where all the sort of functionality within the system is decoupled, one node from the other. So it makes for very composable systems. We can take all these different elements and build them together and very quickly realize different configurations and new capabilities without having to go back and recode everything to support that. So it's a really nice way to design these sort of large-scale distributed systems. Of course, Adobe wants to update in the middle of a talk. Thank you, Adobe. Okay, so let's subscribe to this data, and now this tool in the middle is actually going to become a client, just like the three applications on the right. And I can actually see the data coming in now in real time. I can visualize this data as a sample log, and now I'll actually see the messages scrolling by. So each line in this table is essentially new data coming in from the sensor, and you can see as it changes over time as I move it around. Sometimes a picture is worth 1,000 words, so let's visualize some of that data actually as a time series. And let me shrink down the time base so it's a little easier to see. And so this is the Y coordinate of the ball. And as you can see, as I move the ball up and down, essentially I'm able to see those changes reflected live. And again, the tool had no prior knowledge of what this data type was, but because of the data-centric nature of DDS, it's able to learn the schema, learn the data type, and I can then, just like visualizing fields out of a database, I can visualize fields from my data on the wire and basically plot that. Now, in terms of edge control, one of the things that we would like to do is perhaps, like I said, based on the sensor data, we might want to execute some kind of local control. And that's actually what I'm going to do here. I'm going to fire up a command, just a little command line tool that is basically going to do one additional capability. And that's what we see over here on the right, this Pixie Tracker app. And basically, it is going to subscribe to the circle information, and it's going to publish information back out to the camera to basically direct the camera where to point. Essentially, what this tracker app is going to do is it's going to attempt to keep the ball in the center of the field of view of the camera. So right now, as I move the ball, the camera is static, and you'll notice that the shape moves around on the screen. Once I start Pixie Tracker, it's actually going to attempt to move the camera over the network to keep the ball in a central location. So it'll just take a minute for it to finish its discovery. And once we do that, I should probably kill these guys. Kill some of the additional clients right now. I'm taxing my system with the doing this with the broadcast of the video at the same time. Let me just kickstart that again. I apologize, we're having a little bit of trouble with my network here. Unsubscribe everywhere. 0, that's good. Okay, there we go. So the tracking app is synced up right now. And hopefully you can see on the WebEx that as I move the ball now, the camera is tracking it. And so this is local control. It's happening over the network locally. And you can see it's responsive. I have the response that I need. And basically, this is independent of anything that's going on exterior to here in terms of the cloud. And so this is, ideally the way that we want to create our edge systems. I'm going to start another application here, which is actually going to take some of this data now. And some of this we may want to actually push up to the cloud and see how my internet connection is still slammed. It's still slammed. Okay, we'll give that a minute to come up. Let's go back to the presentation and talk about what we're seeing here. I'm going to put this ball down for a second. I have two hands again. Okay, so the design pattern that we're trying to get working with this WebEx, it's a little difficult right now, is basically one of three design patterns that are recommended by the Industrial Internet Consortium. If you're not familiar with the IIC is the largest of the consortium that are out there for IoT that is squarely focused on industrial applications. And so they recommend these sort of three different design patterns, a multi-tiered approach, layered data bus like we just saw. So the three-tier pattern is very much one that should be common to IT-based folks, and this is basically your sort of standard tiered architecture where we have a bunch of devices out at the edge, and they may communicate to some kind of local gateway. There's a platform tier that may be located on site, may be located off site, and then eventually there's an enterprise tier, which is sort of your cloud level. Data flow here again is primarily north to south. That's basically from the edge up to the cloud. Not a whole lot of device to device communications out at the edge. And again, this is kind of those telemetry type applications. There's this gateway mediated pattern, which is very similar. Again, it's really about sort of aggregating data out at the edge and passing it northbound for some kind of analytics. We might pass a limited amount of data back southbound for doing things like optimization. But again, very little node to node east-west communications out at the edge. This is really about things sort of communicating and pushing data back up into the cloud. It's really not about designing large-scale distributed systems that can work autonomously. And then the last of the big three design patterns, which is the one that we're talking about today, is something called layered data bus. And essentially, that's what we're seeing in things like healthcare, where they have a local data bus within the patient room. Each room has its own data bus. Each of those feeds data back up to some kind of systems of systems, higher level data buses within. So this might go back to, for instance, a nurse's station within one particular area on the floor. That might go back up, then each of the nurse's stations ties back into a higher level hospital system, hospital back-end systems, things that tie to electronic health records, admit discharges systems, and then some of that data might push back to an even higher level. Again, sort of off-site, maybe to some collective health organization that collects data from multiple hospitals. And this type of pattern, a layered data bus, is different than the first two in that it scales both east to west as well as north to south. Like I said, the other ones tend to be very vertically focused. This one is really about scaling horizontally at the edge, but then still allowing this vertical integration. So if you can think about things, applications like healthcare or autonomous vehicles, again, we might have one data bus within the vehicle. This is all our high bandwidth data. We talked earlier that, something like an autonomous vehicle might be spewing out 12 gigabits of data a second. Obviously, we can't push all of that off vehicle through any technology that we have available today. But we do need all of that data shared to multiple places within the vehicle. And that's really where a data bus shines, the kind that we just saw, where we can ship large amounts of data locally in real time on a local network, then downsample some of the data and push it up to the cloud or to higher levels. Higher levels in an autonomous vehicle world might be vehicle to vehicle or vehicle to infrastructure if we have smart roads. So we might leverage that data-centric nature of the data bus to basically do some data aggregation and downsampling here within the vehicle, right? So here within the vehicle, I do know my position and my speed as well as a whole bunch of other things, right? But I don't need to push all of that data up to the next level. I might just need a summary. What is my position and speed and my intent for the next 2 seconds without having to share, for instance, my entire LiDAR point cloud about every single obstacle that I'm seeing? But just sharing my position, speed, and heading to the vehicle-to-vehicle infrastructure can help tremendously to help cars avoid each other at intersections. And we can also communicate a limited amount of data to the infrastructure, to smart roads and things like that, to the city at a higher level, for fleet management, for traffic management, and then at an even higher level up to the public internet for further services that may become available. What's important about this stack is if you were to think about using this stack with most conventional technologies today, a lot of your IT technologies today, or even some simpler IoT technologies, you're going to end up with a sort of Tower of Babel of protocols, software protocols. You might have one protocol going on here in the vehicle, right? You're going to be running CAN bus with AutoSAR or something like that. You're going to have another protocol that's going to be doing your vehicle-to-vehicle and vehicle-to-infrastructure. Still another one that's handling some kind of data management back up to the fleet management and the cloud places. And then as you design your cloud applications, perhaps another set of technology, right? Your RESTful APIs, your JavaScripts, and all those kind of things. And so it becomes very difficult to create these sort of, it's hard enough to create a vertical application like this, which makes it almost impossible to try and create these sort of horizontal applications where these types of systems can talk to each other. The way that you break out of that is you use a technology like a Databus that allows you to use a unified data model and a unified API across every level of the stack. And that's one of the things that DDS brings, is that basically you can use the same technology and the same interface because the data itself is the interface now. It's not a communications protocol. It's not a particular wire level protocol. It's not a specific set of bits and bytes in a specific order. That is the interface between all of the applications, both horizontally and vertically in this stack. The interface is the data model itself. And when I say data model, I mean things like, what's the current status of a car? Tell me its position, its heading, and its speed. That is a data model. In terms of healthcare, it's the exact same thing. What's the data model for a patient? The data model for a patient is basically 5 vital statistics. Tell me about their heart rate, their respiration rate, their body temperature, their blood pressure, and their blood oxygen level. And that is the same data model that's used for a patient in all kinds of different systems today that don't talk to each other. There's no reason that they shouldn't talk to each other if they're all using the same data model. That's what a Databus buys you, is a technology for creating IoT applications. The data is the interface rather than the protocol and the bits and the bytes and what kind of network am I using. So that's the real benefit of using a unified data model across every system. You notice the design pattern here is exactly the same for healthcare as it was for autonomous vehicles. And we see this design pattern used over and over and over again in these autonomous systems that need to scale both horizontally and vertically. If you look at a truly huge system, one of the areas that we work in, we run the launch control system at NASA Kennedy Space Center. And it's essentially just those same 2 use cases you saw before for hospitals and autonomous cars, but on an even larger scale. This is the world's largest control system, the world's largest SCADA system. And they do over, when they fire off a rocket, it's over 500,000 data points per second worth of information that they are sharing across miles and miles of the launch area. The launch area is essentially a large chemical factory that they manufacture the chemicals and dump them into the rocket in the days and hours leading up to the actual launch. And as they do that, they can't miss any of the data. They have to collect it all and save it. Every single message that gets sent has to be archived so that they can do their processing on it later on. So let me see if we can get how our internet is working today. And if we have any data going back up to the cloud. So we are publishing. Let me see what we're getting here. I'm going to turn off the tracker actually, temporarily. So I keep my hand still. Let's get this guy subscribed. Okay, so we have data flowing there. Not quite sure why it's not getting to routing service. Bear with me half a second. So Caroline, while I'm trying to get this up and running, are there any questions that we've had so far?
Hey, John. Yeah, we have quite a few. We will start with one here. Let's get these rolling. Do you have any experience for how regulatory agencies such as FDA/UL/CSA treat the verification/validation requirements of distributed layer architectures versus simpler sensor to cloud architectures?
Yeah, that's a great question. Obviously, validating a large-scale system is a much bigger task than a small-scale system. There are a number of different approaches that folks that we worked with. We do a lot of work in the medical space on things like surgical robots and advanced patient monitoring and advanced medical imaging, the latest 3D CAT scanners, and different manufacturers have taken different approaches. In terms of where we fit into the ecosystem for that, some folks have taken the approach of what we call SOUP, right? Software of unknown pedigree. And they have a process in place for essentially certifying the system as a whole with integration of SOUP, right? And that could be things that are based on like a Linux operating system where nobody's going to take the entire operating system and get it certified. And we're just kind of an extension of that. For other folks that are doing sort of higher level classifications, maybe something like a class 3 medical device, in that case, you may actually want software that carries some kind of safety certification as a component of your system. It makes the overall certification easier. RTI, we do have a version of a Databus that has been through functional safety certification for various industries, and we have a certification evidence package. The industry that we developed it for was actually for the FAA. For flight avionics. And that is pretty much the gold standard of safety certification. We've gone through FAA DO 178 level B certification we've been through, but the evidence is actually up to level A, which is the highest level. And so any certification, any other certifications like UL 61508, ISO 13485, some of the medical ones, those are basically down certifications from what we've already done for applications like FAA. So there are a couple of different approaches. You can take the sort of system level approach and just sort of take the, hey, we've got a bunch of soup in here, or you can actually start with known certified components. It really depends on your corporate path and how you intend to go to market with that kind of thing.
Thanks, John. Would you like another question, or are you ready for
Sure, go ahead with another question.
Awesome. What is the data standard format that is output from the Raspberry Pi?
The data standard format, there isn't a standard format. So it is using DDS, which basically DDS creates the data bus, and DDS is essentially allows you to bring your own data model to the party. right? So if I take a look at this data and the publisher, here the Raspberry Pi, you can see this is the data model that I have defined. And I defined this in this case for the demo, right? I said, this is how I want to represent the status of this. That being said, you can bring your own data model, and many industries already have existing data models today. So in the industrial space, there's things like SIM, the Common Information Model, and you can take components of SIM and drop them into this, and basically DDS will carry your data models. The data models tend to be tied to specific vertical industries. So we see ones in the energy space, things like Open Field Message Bus. We see ones in avionics, things like FACE, Future Airborne Capabilities Environment. There are some efforts in the medical space for standards like OpenICE, Open Integrated Clinical Environment. There's other data model standard formats that are in things like modeling and simulation for technologies like HLA and DIS. So really, you can kind of bring your own data model to DDS. It's a great standard to build other standards on top of. If you are looking to create an open standard within your industry and you have an idea of the data model and semantics you want to apply there, DDS allows you to express that. It's a great question.
Thank you.
Yep.
Thank you. I have a three-part question here. How does the content stack become informed of new data types? Do developers have to prep and update the content stack? And does it have to know and also tell the other communicating parts? Sorry, it froze for a second. Communicating endpoints what the data type is.
Okay, that was a bunch of really good questions. Could you start with the first one?
Yeah, absolutely. The first part was, how does the content stack become informed of new data types?
Okay, so basically what happens is that every participant that comes on the network knows about its own data types that it's interested in, which ones it's going to publish, which ones that it's going to subscribe to. There is a discovery process that happens at runtime, and you can see evidence of some of that on my screen here, right? Basically, all of these applications, as I start them up, they all discover each other and exchange information about their data types, as well as something called quality of service, which you see over here in the panel on the right. And this is quality of service is basically how a publisher advertises a certain level of capability. Hey, I'm a sensor and I'm offering to publish this data. Here's the schema, right? This is the data format. And here's how I'm offering to deliver to you. I can give it to you best effort, or I can give it to you reliably. I can offer you a deadline, basically a maximum spacing between subsequent messages. So you're always going to get an update from me at least every 100 milliseconds, as a for instance. Receivers also advertise interest in topics and types. Basically, I'm interested in getting this sensor data. I want to know about the shapes. I need to know about them, and then they get in a certain way, and they express their quality of service. And again, that can include things like ownership, like reliability, like deadlines. These are all kinds of things that different subscribers to the same information can basically ask about. So the data model, the schema, is shared during the discovery process, as is the quality of service. One of the unique things about DDS is, when it comes to sharing schema, there's a couple of different approaches. The first approach is that basically your schema is locked down, everybody knows it ahead of time, and so you don't need to share it during discovery. The second approach is I'm going to send the schema with every message, right? And this is kind of the XML approach, where every message I send you has a bunch of XML tags that specify what each field is. That becomes very expensive because you carry a lot of overhead to share a very little bit of information. To send a single integer, you might have 100 bytes of overhead. DDS mixes the two approaches. The advantage of sharing the schema with every message is that anybody can get any message and figure out what's in it. The advantage of the first approach is that everybody kind of knows ahead of time, and it's very terse on the wire. It's very space efficient. DDS is a mixed approach. It shares the schema once during discovery. Once both sides agree on what the schema is, now we switch over to a very terse binary format that's very, very efficient at runtime. So you can see a couple of numbers here on the screen. The first is this type object size, and this is basically 1,060 bytes is how big the representation, the schema for this data type is. We do that once during discovery. At runtime, we can get our sample size, again, we switch to that very terse binary format, down to as small as 28 bytes, as long as 160, depending upon how long the string is that somebody uses for the color. So that's the balance there. So that was a great question about how do people learn about different data types and when are they shared. What was the second part of that question?
Thanks, John. Yeah, the second part was, do developers have to prep and update the content stack?
They have to, what was the, did you say?
Prep. Do developers have to prep and update the content stack?
I'm not sure I understand that question.
Okay, well, we'll move on to the third part of the question was, does it have to know and also tell the other communicating endpoints what the data type is?
Yeah, I think we covered that in the first one, right? You can share the schema information dynamically at runtime, right? So applications don't need to have any prior knowledge of each other in order to communicate. So this tool, for instance, that we're looking at, it has no prior knowledge of what any of these data types are and what kind of applications. I can plug this into any of thousands of applications today that are running DDS, and it will learn the data types from the wire for that specific industry and that specific application. And by the way, these data types can grow and evolve over time. You'll notice that there's some tags in here that say they're extensible. And that means that this data type can grow and evolve. Actually, as part of the standard, as part of the strong typing system for DDS, is this ability to grow and evolve your data types without breaking back compatibility. So let's real quick move along to the demo. Of course, I know we're a little long on time. So essentially, I'm going to fire up some additional components here if I can get my wide area network to work. So down at the bottom, we have the local data bus that was running. I'm going to fire up this instance of routing service, which is going to create another data bus out to the cloud, an instance of Amazon Web Services, where we have another instance of our routing service working. That's going to create another data bus out in the cloud that's going to talk to something called our web integration service, which is then going to present a RESTful API out to the internet. And I invite any of you that have a smartphone to go ahead and point your phone at that QR code. And if you are able to pull up that web page and see anything, do me a favor and put something into the chat window for Caroline just to let us know that you're seeing it. Caroline, if you could let me know if anybody's seeing it. Hopefully, what you're seeing in your web browser looks like my web browser here, or I'm actually seeing a copy, a little bit laggy, but I'm seeing a copy of what's actually happening here in my local data bus. Anybody able to see that? Anybody able to pull that up on their smartphone?
I'm getting a lot of responses here, John, and I have it up on my phone. That's super cool.
Yeah, so one of the things that you should notice is obviously it's a little laggy, right? I mean, relative to this panel in the upper right on my screen is fairly responsive. What's happening in your local web browser is going to be a little bit behind that, right? And this goes back to that problem that we talked about earlier with trying to do, control up in the cloud, essentially. There is some latency, a little bit of lag, and so it's not great to be able to send my local data up to the cloud and attempt to do control up there and send the control messages back out here in the edge. It's just not going to be fast enough for a lot of applications. And as you saw earlier, the communications can be a bit intermittent because you don't know what else is going on. In my case, my whole neighborhood is working from home now. I'm trying to run a WebEx that's going through the same pipe. So if you're on a hospital network, for instance, there's probably a good chance that there's some video conferencing going on the same pipe that's going up to the cloud as the one that you're trying to send your patient information through. So generally speaking, you want to try and do your control locally out at the edge. as we saw here, a local data bus. Then you want to maybe take some subset of the data. For instance, I'm not sending the whole history up to the cloud that I'm using out here at the edge. And then, you know, some other basically level of data that, you know, you're going to present to perhaps a RESTful API to some kind of web client. So that in a nutshell is the layered data bus in action. We've got 1, 2, 3, sort of 4 different layers of this data bus, right from a local one that's here on my desktop executing, you know, just the local components talking to each other, and again, pushing that data sort of up into the cloud. So that in a nutshell, like I said, is layered data bus in action. I appreciate all of you that sort of logged on at home there. And essentially a data bus is really a data everywhere abstraction. And one of the cool things about it is that it doesn't actually send all of the data to everybody at the same time. Essentially, every application gets just the data that it wants, just when it needs it. And that is really one of the neat things about a data bus, is that we don't have to send all the data everywhere. And what's interesting about that is this kind of architecture is sort of naturally, massively, inherently parallel, because I'm only sending data peer-to-peer to just the clients that need it, as opposed to sending it to everyone or sending it all back to a server. These types of systems tend to be able to scale to very large sizes very easily, because there is no single choke point, no single point of failure. So again, RTI makes a really cool data bus based on an open standard called DDS, Data Distribution Service. The standard is owned and stewarded by the Object Management Group. These are the folks that bring you other cool standards like UML. We provide a whole suite of tools to go along with the data bus for your development. And again, I think that, you know, using this type of technology for applications like intelligent connected healthcare, where these types of systems can begin to work autonomously, can begin to take a lot of mistakes out of the system, can begin to remove a lot of risk from the system, not just for the patients, but also for the caregivers like my niece, who are, you know, potentially put at risk by having to go in and fiddle with all these devices, you know, right next to a sick patient. So this is really the promise of you know, the smart machine era of the industrial IoT. So as a call to action as we wrap up, I will tell you that you can get a full trial version of our communication stack. It's called Connect DDS Pro. You can go to rti.com/downloads and download it. Once you do that, you will likely get a phone call from one of these folks. These are some of the folks that I work with. Lisa is an account manager. She is based near me. I'm in the Raleigh-Durham area, based in Cary. Lisa's based up in Chapel Hill. Ken is my counterpart on the applications engineering side. Ken is based in Northern Virginia. I'm John Breitenbach. I'm there on the right. That is back when I was still able to get my hair cut. Obviously, I'm a little shaggier today. But feel free to reach out to any one of us if you have any questions about Connect DDS or about IoT applications in general. These are different places that you can connect to RTI and follow us on all your favorite social media as you are locked up at home. And again, I just want to say thank you to Caroline and the rest of the Riot folks. We love working with the Riot folks. We've been working with them for a lot of years. They have some really cool events. It's really a neat community. I invite you to reach out, connect with me either directly through email or on LinkedIn. And at this point, Caroline, I guess we'll open it up for any further questions that happen to come in.
Great, John. Yeah, we do have a couple more. Does the database, or excuse me, the data bus work with LF Edge X infrastructure?
LFX Edge, that is not one I'm familiar with. I'm sorry. I'll have to get back to you on that. We'll take that question offline. How was it spelled? LF?
Yeah, it's capital L.
Take a note.
Sorry. Capital L, capital F, and then Edge, capital X. And Scott, we'll make sure that John connects with you about that particular question.
Yeah, I
Scott
apologize. That's not one.
Yeah, Scott is saying that it's from the Linux Foundation.
Okay.
Next question, are there open source examples of layered databus?
Let's see, open source examples. There is an open source implementation of DDS. Like I said, you know, we sell one implementation of it. We are a commercial implementation. DDS is an open standard, and I do want to make the distinction between open standard and open source, right? An open standard is something like TCP or DDS. It is a standard. There's a standards body that owns and stewards the standard. Because it's open, you can join the standards body, contribute to the standard, help steer its direction. Open source is basically a commercial model of distributing software. So that being said, DDS is an open standard. It used to be a proprietary standard. It was an RTI proprietary product. We showed it to the Navy back around 2000. They said, we love the technology. We don't want to be in the middleware business. If you, RTI, will make this an open standard with our sponsorship, take it to the OMG, and essentially create competition for yourselves, we'll standardize on it. So RTI's management decided that that would be ultimately a good thing for the technology if it was an open standard. So that's how DDS became an open standard. There's 12 different implementations of DDS today. One of those is, one or more are open source. They don't come with the full suite of development tools like some of the tools that you saw me showing earlier, but you can absolutely get an open source implementation of DDS, and that will allow you to build your own layered databus.
Thanks, John.
If you're looking, I will just add that if you're looking for a turnkey example, we do have some. If you go to our website and scroll all the way down to the bottom of our web page, there's a link for something called Case Plus Code, Case and Code, and those are fully baked examples that show a layered databus. And you know, they're explained. You can take a look at those and see how the layered databus is put together.
Thanks, John. Next question. Edge control / data systems require local-based support. So most corporates outsource these to the cloud for financial reasons. So this gentleman is just wondering how that works.
I'm not sure I follow the question. Can you clarify what you mean by, could you read that again, Caroline?
Yes. So the question was, edge control / data systems require local-based support, which most corporates have outsourced to the cloud for financial reasons, and then they're just asking for a specification on how this works. But we can get you connected to him separately, John, if you need a little more clarification on that one. Cool. We'll move on to the next one. What is the open source GitHub URL for the implementation?
You mean this, I assume that you're talking about the standard. So if you just Google OMG, short for Object Management Group, OMG space DDS space portal, that will take you to the OMG's website for the standard, and from there you can download PDFs of the various standards that make up DDS. I will say DDS is not a single standard; it's actually a family of standards. I think there's about 13 or 14 different documents. Some cover the wire level protocol, some cover the upper level API, some cover security, some cover data modeling. So there's a number of different standards there, but they are all open. They are freely available from the OMG website, as opposed to, I know some other standards you have to pay to, you know, $150 or something to get a download of the standard. With DDS, it's all freely available. And if anybody needs a link, shoot me an email and I will send out links later. Maybe I'll just post them to through Riot's meetup page or something like that.
That would be great, John. And as a reminder to everyone, this video recording will be also posted to Meetup as well. And we'll just take the last question of the day here, John. How long does discovery take? If a new device comes online, does it have to learn all the data types of the DDS content stack?
It does not. So in large-scale systems, obviously, discovery is a function of the number of participants that are on the network. There are settings that you can put, and one of the reasons that people do a layered data bus is to essentially also limit the amount of discovery that has to go on at any given layer. And that's one of the reasons that that pattern exists, is very specifically to partition data flows, to limit who can see who. That being said, there's a lot of knobs you can turn within the discovery process. You can discover everybody everywhere, or you can just discover one specific person at one specific IP address. You can lock it down as much as you like. We have the ability to do, for instance, asymmetric discovery, where I can discover you, but you can't discover me. So essentially, it only happens one way. We have the ability to support discovery through a third-party rendezvous point, something that we call cloud discovery service. So basically, every node just has to go to that one point, and that one central server is sort of the clearinghouse for all discovery information. There are certain times that use case makes sense. But basically, I don't have to learn about everything in the system. I only have to learn about other participants in the system that have data that I am interested in, or that are interested in my data. And that happens through a two-part discovery process where participants first discover each other. And again, that can be limited. And then once participants discover each other, we share endpoint information. Here's the topics I have, you tell me your topics, and we decide if we have something to talk about. In terms of the schema and the data type being shared, that is actually purely optional. And there are some knobs that you can turn there as well. You can turn it off completely. If you have a bunch of closed system where everybody has the data types and knows them ahead of time, and you don't want anybody else to be able to snoop the wire and discover what that is, you can disable that completely. You can also cap it, where you basically say if a data schema type is above a certain size, don't share the big ones. You can share the little ones, but not the big ones. So there's a lot of different ways that you can approach that, both in terms of limiting who you're talking to, how you're talking to them, which of the schema types you're going to share, and then there's some other logical partitioning that DDS offers as well, something that's called the DDS domain and partitions, which are ways, again, to sort of separate discovery and who can see who on a particular network. So that's a great question, and obviously it's asked by somebody that's probably designed large-scale systems before. You don't know to ask those kinds of questions unless you've been through that pain.
Awesome. Thanks so much, John. I encourage anyone, if you would like to connect with John further, please reach out to him via email or LinkedIn, or you can always reach out to me as well. But thank you all for being here today. I really appreciate your time, and special thanks to you, John. Stay dry.
Thanks, Caroline. Thanks, everybody. Stay healthy.